Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Vivek Kumar. He's a principal investigator of his own lab called Kumar Lab. We're going to talk about his work with hydrogels for tissue and blood vessel regeneration. Vivek is the co-author of over 50 peer-reviewed journal articles, over 5 dozen abstracts. He's co-inventor on over 12 patents and applications, and he's been a serial entrepreneur. It's 4 startups to date. He currently holds academic appointments at New Jersey Institute of Technology as an associate professor in biomedical engineering, chemical and materials engineering, and biology, and at the Rutgers School of Dental Medicine in the Department of Endodontics. Vivek teaches biomaterials and biomedical translation and entrepreneurship. So Vivek, welcome and thank you.
Thank you very much for having me. Thank you. Quite an introduction. Thank you.
Yeah. Well, tell me a bit about your background and how you got to this current startup that you're working at.
So a lot of the work that I've been doing over the past decade and even in my graduate school training has focused on the development of blood vessels. Now, during graduate school, I worked with a surgeon who looked at larger blood vessels, things that for bypass surgery, for example. And further in my training, I looked at microvasculature, regenerating small blood vessels like the types that you see in your eye when you rub it too hard. And now that I'm faculty, I'm a professor, I have my own students. And some of the questions we ask is, how can we use these microvessels, this microvasculature, that we can use materials, injectable materials to regenerate? How can we use this to treat disease? So one of the diseases that we're very interested in is dental pulp regeneration. So when you need a root canal, they remove the soft tissue in a tooth, the infected stuff, and they put in rubber rods. So the tooth is left inert and not responsive to future infection. So what we do is we inject our angiogenic hydrogels, these hydrogels that create blood vessels. And we've shown in a large animal model in canines and dogs that we can regenerate blood vessels within the tooth. Now, interestingly, we've done this for a number of applications, including regenerating or preserving cranial tissue, brain tissue after injury in the brain, heart tissue after myocardial infarction or heart attacks, and even limb tissue after poor circulation in the legs. So I know there's quite a bit of stuff. I'm happy to chat about the details of any of that.
Sure. Yeah, I know that even when you're dealing with small geometries in the body or in living systems, it's very hard to get blood vessels to regenerate, nerves to regenerate, et cetera. So the hydrogel is acting as what, like a scaffolding for the blood vessels to innovate.
Right.
So that's the right term.
Right. I think, when we think about tissue regeneration, one of the best, or tissue engineering, tissue regeneration, one of the first things I like to think about is healing, right? How does the body do it by itself? How does the body heal a wound? How do babies, I just had one, right? How do babies heal so well when adults, especially elder adults, our aged populations don't heal as well? Wounds, eyesight, stem cells, things like that. So in understanding native polymers, circulating in your blood, circulating in my blood is a polymer or a pre-polymer, a piece of a polymer called fibrinogen. When you get an injury, that fibrinogen cleaves. Long story short, you get a fibrin clot. You get a polymer clot that traps red blood cells. That scab that you get is a protein polymer clot trapping red blood cells. It's reddish brown or black because it traps red blood cells, and it's otherwise a white clot. Now that fibrin clot dissolves within 3 to 5 days. Now, for a young kid, that's more than enough time. They have good stem cells, they regenerate quickly, young animals as well. But for older animals, older adults, it doesn't regenerate as quick. And what we've designed is a hydrogel, a protein that degrades slightly more slowly, right? So our materials degrade over 3 to 4 weeks as opposed to 3 to 4 days. And our materials contain a signal. So the message is within the medium itself, right? There's a signal within the material that promotes blood vessel growth. So we have an angiogenic signal and a scaffolding for cells to infiltrate. If all of that made sense.
Yeah, no, it makes sense. For young animals, and you said for kids, 3 or 4 days of, fibrinogen clot that attracts red blood cells is enough. But what about for older animals and older adults? And yes, I know it's variable, but what's the time scale approximately needed?
So to put it fairly, when a wound occurs, be it in a small or large animal, in a young or old animal, the wounds heal very differently depending on other diseases, depending on age, and depending on the location. For example, a wound in the eye or on the skin, on the face, for example, would heal very differently than a wound in the kidney or the liver or in a different area in the body. So in general, the same wound would take longer to heal in older adults. And it's primarily, at least in my opinion, because in younger animals and younger humans and babies, their tissue has younger stem cells. They proliferate more easily, and there is faster clearance. There's not as much scar tissue. There's not as much aged tissue. But I don't know if there is a defined perfect time for scaffolds to promote regeneration. And I think we're seeing that in some of our results. In some of the studies that we do, we see that the scaffold needs to be there slightly longer, on the order of about a month to 3 to 6 months. And for some of our studies, we see that we want them to degrade even faster, in less than a month.
All right, so you somewhat remove the time constraint. In older animals, again, and in older people, is the scab being present there for longer enough, or what else needs to be brought along with it to help them?
Right. I think you hit the nail on the head right there. So when we do these surgeries in canines, for example, when we put in, when we just induce a blood clot, or when we just put in scaffolds that don't promote regeneration within the tooth space, what happens after a month is that root canal, that space within the tooth, is empty. It's devoid of tissue. There might be a small little residual blood clot, disorganized tissue. Nothing's really in there. On the other hand, when we inject our hydrogel scaffolds, we see native tissue grow in, degrade our scaffolds over a 3-week period, and replace it with tissue. I mean, think about it this way. If you're building a building and you've got some really good builders, maybe 3 days is enough. So you put up your scaffolding, they come in, they build a building, and they're done. On the other hand, sometimes the builders are not as efficient. They're a little bit older. They take a little bit longer. If your scaffold sticks around for 3 days, you're going to get 1 floor of that building. If your scaffold sticks around for 3 to 4 weeks, in addition to providing sufficient oxygenation, blood vessel regeneration, and guidance for the tissue, if you can provide the right cues from the material over a longer period of time, in my opinion, that's what leads to sustained tissue regeneration.
But it's not just the time. It also sounds like the hydrogel is providing this necessary scaffolding, and for some reason prevents the fibrinogen from getting in there and setting up shop and acting as a scaffolding. And that's why the healthy tissue goes in there more often with the scaffolding than not. The reason is.
So coming back to it, I think fibrinogen degrades much more quickly. So you're not giving, or the body or the tissue is not being given enough of a chance or enough time to repopulate that scaffold. Now, that being said, there are scaffolds that you could put in that will never go away. I think a classic example that I teach in my biomaterials classes are hip implants, for example. In Indian culture, we cremate the deceased. And I remember my mom was telling me about my grand auntie, I think. They burnt her body after cremation, and all that was left in the cremation pyre, I think it's what it's called, pile, was her total hip implant, right? Or total knee, one of the two, because those implants are made of metal polymers, which don't degrade or go anywhere. So in reality, I think tissue regenerative scaffolds need to provide certain cues temporarily, but need to find that sweet spot. So coming back to what you were saying, our scaffolds are protein-based. They're short proteins, they're peptides. And what's neat about them is that they aggregate, they come together on their own. It's called self-assembly, right? Fancy word. They come together on their own to form fibers. And what's neat about these fibers is that they entangle into gels, kind of like Purell. But unlike Purell, which is antimicrobial, contains a lot of ethanol or alcohol to kill stuff, our hydrogels contain a signal to promote blood vessel growth. Now, one of the other things I teach my students is that there is a blood vessel every 200 to 300 microns from each other, right? In order to perfuse all the tissue, to provide blood supply to all the tissue in the body, blood vessels, capillaries need to be about 0.2 to 0.3 millimeters away from each other. The only way you can do that reliably, 3D printing, all these fabrication techniques can try to get there, but don't really do a good job. The only reliable way of getting there is to create scaffolding which has instructive signals. Yeah. Hopefully that makes sense.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
Well, I was going to say some of the scan, like the hydrogel, is not going to produce, let's say, exosomes to signal near tissue and stem cells and recruit them. The fibrinogen likely does, because it is living material for a while.
So that's a great point. That's a great point. So fibrinogen is a native protein that has many different domains. It's a large protein. And when those domains are cleaved, they have subsequent domains that activate cells, cell adhesion, proliferation, what have you. Now, our scaffolds, similar to fibrinogen or other collagen, fibronectin, structural proteins in the body, similar to that, our scaffolds contain a domain from vascular endothelial growth factor, VEGF, right? It's this growth factor, it's this molecule that helps the body create blood vessels. But what we did was we took a small piece of that large growth factor and we stuck it onto our proteins. So now when this protein, when this peptide self-assembles, you have this angiogenic signal, this VEGF signal, this blood vessel forming signal at very, very high density. So when we inject it, we localize that signal to wherever we put it. You know, this idea of putting signals into the body, that's not new, right? Most recently, we've seen Moderna use mRNA to ask the body to get muscle cells, to get cells to produce different pieces of viral code for antibody production. Similarly, people have been injecting growth factors, cytokines, chemokines, stem cells, what have you, for decades, since the early 90s or even before that. The challenge is, every time you put all these factors into the body, there's no reason for them to stay in one place, right? You put in a bolus of saline, you put in a bunch of liquid in the body, it diffuses away, it clears away. The advantage of our scaffolds is that they self-assemble. They come together on their own. So they form a bunch, they form a bolus where we inject them, and you have sustained local signaling for on the order of weeks. So that's another added benefit of our injectable VEGF mimicking angiogenic scaffold.
Okay, so you believe you've isolated the factors that recruit the right materials, stem cells, et cetera, to come and heal the injury?
So interestingly, we have recruited the cells that promote blood vessel development, and we see a lot of mature blood vessels infiltrating these scaffolds, right? So we put a gel in and we see a bunch of blood vessels grow into this gel. So then the question is, what can we use this for? So we know we can perfuse tissue, we can get blood supply in, so we can nutrient exchange, stuff that grows in will survive. Good. Now can we direct the tissue towards a particular phenotype? Can we drive that tissue to become bone, cartilage, fat, stems, or muscle? Can we drive the phenotype of cells infiltrating? So right now in my lab, some students are working on putting this angiogenic signal, this signal that helps create blood vessels. And I have other students that are looking at putting myogenic signals, signals that promote muscle regeneration, neurogenic signals, osteogenic signals, neuron preserving or regenerating signals, or even bone forming signals. So far, we've published some work in traumatic brain injury, where we injure the brain of rats, inject our hydrogels, and show good preservation of neurons. I wouldn't go as far as to say regeneration, which is a tall order, but at least preservation of neurons. We've injected this into the eye to treat wet AMD, wet age-related macular degeneration, the leading cause of blindness in above 55, people age 55, I believe. We've injected this into the legs of mice and hearts of mice after heart attacks and poor circulation of the legs, and shown good regeneration of musculature and vasculature, blood vessels and muscle, and survival. And we're very interested in hopefully one day taking this towards the clinic. To take a drug or a product into the clinic, you can do all these fun, fancy, interesting, cool experiments to show that it works for different applications. But one of the biggest challenges, and that's where some of the work that I do with my startups comes in, one of the biggest challenges is what we call the valley of death, where you have this neat technology, except you have these run-of-the-mill, they're called ADMET, absorption, distribution, metabolism, excretion, toxicity, your run-of-the-mill ADMET and manufacturing, CMC, chemistry, manufacturing controls, manufacturing toxicity studies that every drug needs to do. That costs on the order of $2 to $3 million. And typically there's very little value creation outside of the fact we can manufacture this and it's safe, which one should know if they're doing efficacy studies anyway. Long story short, we've demonstrated efficacy for many indications, for many different diseases and conditions. We're trying to raise funds to do toxicity and manufacturing studies, and then hopefully take this into first-in-human trials.
When the blood vessels have grown back, like you gave an example of the canine's tooth pulp, do they have the same branching as maybe other undisturbed teeth? Do they have the same width and morphology and all that, or do they look different because they're maybe composed differently?
So what's interesting is that the blood vessels that infiltrate these scaffolds are very mature. So if you think about a blood vessel, the smallest blood vessel in the body is a capillary. It is a single cell, endothelial cell lined tube, right? In many cells forming this mosaic patchwork of a tube, right? That is single cell lined. Now, those are immature vessels. Obviously, they're single cell wall, they break easily, right? And you can mature those vessels by putting smooth muscle cells around these endothelial cells, parasites as well, but let's not get too complicated. And you create these stabilized, muscularized blood vessels, right? So what's interesting is that the blood vessels that we regenerate are not nascent, immature capillaries, but mature, robust, muscularized blood vessels. Now, to be very clear, we're not generating 1 millimeter, 5 millimeter, 10 millimeter diameter blood vessels. We're not regenerating the aorta. We're not doing that. What we're regenerating is microvessels, the kind of vessels that you see when you rub your eye, right? So small microvasculature. Answering your question specifically, the types of vessels and the density of vessels that we see within these implants is even greater in terms of maturity and density than we see in native tissue, right? So we see more blood vessels and better maturity of these blood vessels. However, we don't see edema, fluid buildup, or leakiness of the blood vessels. So we see the vessels infiltrate, perfuse the tissue, but they're not leaky and they're not, causing swelling or what have you.
How do you make sure that the blood vessel formation is localized and kept to the right spot? Does it not migrate beyond the hydrogel?
That is a fantastic question. And that's one of the biggest questions we get from venture capital investors. And even one of the most recent grants that we submitted, that was the feedback that we got from one of the reviewers. You're putting in a signal that creates blood vessels. One of the first things that comes to mind when you think of creating blood vessels is cancer, right? What if you couldn't that cause cancer? Now, our first rebuttal against that is you can have all the highways in the world, but cancer requires cancer. Cancer requires malignant cells. Cancer requires cells that are cancerous. Even if you have a blood vessel network, the cells, if they are not cancerous, you're not going to get malignancy or cancer, first of all. Second of all, over the past 10 years, every single implant we've put into any animal model has not resulted in malignancy. So we've tested it for safety as well. But most importantly, the signals that we put in self-assemble, right? So if you remember, I told you earlier, these signals come together on their own. They aggregate like collagen, like elastin, like Jell-O, right? When you make Jell-O, you heat it up, you stir it, and when it cools down, all those different gelatin strands aggregate, they self-assemble into a network. And just like Jell-O, our hydrogels self-assemble into a hydrogel. So you can syringe, aspirate, pull up into the syringe, inject it, and it forms a gel where you put it. And this gel stays there, whether it is under the skin, in the muscle, in the eye, in the brain, in the tooth, in the heart, in a bone defect, or all the different models that we've tried in rodents and in canines. It stays where we put it. It doesn't jump into the circulation or anything like that.
Yeah, no, that's excellent. I've read about, for instance, when people have problems with the cardiovascular system, that the microvasculature around the heart actually is what carries in aggregate 90% of the blood, and also that stents don't seem to have the effect that they should, probably because the microvasculature is being ignored. Is there any way that you could recreate properly the microvasculature around the heart, even in small sections? Or is that a huge, enormous geometry type of project?
Fantastic question. And in fact, if you caught me in the meeting right before we did this, I was discussing our latest results in rodent model, where we induced a heart attack, injected our hydrogels plus minus stem cells, and looked at the animal's hearts at 1 week and 1 month. It's a preliminary study. Data is coming out right now as we speak. But basically what we see is that these hydrogels, when we inject them into multiple sites in a heart after a heart attack, promotes blood vessel regeneration. So that's the first step. You're providing highways for the injured tissue to recover. One of the biggest challenges in the heart after a heart attack is that the tissue is infarcted. It starts to become necrotic. It starts to die. You have this patch of heart tissue that's dead. So you can poke it and inject the hydrogel in multiple spots and regenerate the tissue. Now, one of the challenges is, sure, you can create highways, but you need the cells to regenerate heart tissue, which is why we've also tried delivering stem cells along with our hydrogel to promote viability of stem cells in the heart muscle. Interestingly, we're seeing that at 1 month time points, we don't even need cells. We're seeing, and I should wait until we have significance in a published paper, but at least preliminarily, we're seeing that these hydrogel scaffolds alone are sufficient in promoting blood vessel regeneration, and maybe even promoting some of the cellular content that's required for regeneration. All of that said, this is in mice, and people have done a lot. People have cured many, many, many cancers and heart diseases and everything else in mice. And tomorrow, hopefully, we'll be at the stage of testing this in a large animal model, like a pig model. And in those models, what you're looking for is whether you can preserve heart tissue. Now, one thing I want to be very clear about, as I mentioned earlier, we're not regenerating large blood vessels, 10 millimeter size vessels like the aorta or even the coronary arteries. The coronary arteries, if they get blocked, you can stent them, you can bypass them. It makes sense. But the micro vessels, the stents, they don't even make stents that small. And if you made a stent that is a millimeter or sub-millimeter, they will clot very, very quickly. So it's almost pointless. So in reality, there is no good technique to regenerate microvasculature in the body. And right now, that tissue just goes unperfused, just goes without blood. And
because you can't, it's kind of a different injury. It's blocked. Have you ever tried to put these hydrogels in front of a clot or behind, in front and behind the clot?
So we've been interested in treating the blood vessel as a tissue itself, but when it comes to a clot, it's a different ball game. So I did my PhD in larger blood vessel tissue engineering, right? Small diameter blood vessel tissue engineering on the millimeter size. And the biggest challenge there is you want to prevent any clot from forming, because that's going to stroke the patient. And you want to prevent any restenosis or too much tissue tissue ingrowth on the surface of the grafts. And the challenges here are dealt with very, very differently. For example, stents, they contain chemotherapeutics. They contain Taxol, for example, because you want to kill any tissue that's growing on top of the stent to prevent re-narrowing of the blood vessel. Of course, the challenge there is that once that drug fully elutes, that drug-eluting stent becomes a regular stent, and there's new tissue that grows on top. So there's a lot of different challenges, and I don't think we are a replacement for stents or bypass grafts. However, for many, many, many patients, especially those of advanced age, 75 and above, they're not great candidates for surgery. They have poor circulation. It's called ischemia, poor blood circulation. And we think introducing or promoting microvascular regeneration may help them get up on their feet at the very least, hopefully.
What about if you were to construct a bypass vessel or remodel it before it's put back in? Maybe you could, again, remodel it if it's an existing piece of vessel to be used as a bypass, or could you generate one from scratch with the right scaffolding? Because if you could do that, that would be a great solution, at least for the larger vessels.
We should have you write our grants with us. In fact, in 2018, I wrote a grant to the NIH where we said, hey, look, a blood vessel itself needs blood vessels. So an aorta, the largest blood vessel in the body, has a thickness on the order of about 1/10 of the diameter. So about 1 millimeter, about 0.5 millimeter to 1 millimeter in thickness, right? The blood vessel wall itself. And if you remember from earlier, I told you tissue has capillaries every 0.2 millimeters apart. So long story short, your aorta has a blood supply of its own. There are blood vessels coming off the aorta, going into the walls of the aorta, perfusing it, right? Interestingly. It's called vasa vasorum.
Yeah, that's interesting. Huh.
Yeah. So answering what you were saying, we wrote a grant where we said, let's take our angiogenic hydrogels, soak that into vascular grafts, and see whether we can create an artificial vasa vasorum to promote better blood vessel formation. Now, there's a number of different issues. There's a number of considerations that we need to take into account. That grant wasn't funded. We got funding for other stuff. But long story short, I think that is a true frontier that I am very, very excited about exploring maybe in the next couple of years.
Yeah, very, very interesting.
Fantastic idea, though.
Well, good. I hope you guys make a lot of headway with it. Do you know if anyone's been able to map the microvasculature, any part of the cardiovascular system or around the heart? Does it have a certain patterning? Is there anything you can discern from that?
The heart is one organ where looking at the blood vessels is interesting. It's neat, looks nice. Even the brain, you see all these architectures. But there's some really, really cool work being done at Baylor College of Medicine where they're using tissue clearing, right? So they use these different chemicals to clear out all the tissue except blood vessels. And they've imaged the eye. And if you take a look at the vasculature in the eye, it is beautiful. There are so many different layers of blood vessels, types of blood vessels, and maturity of blood vessels that supply different parts of the eye with blood, which are intricately involved with vision. Coming back to what you were saying, the heart has a very, very interesting and unique architecture. I remember when I was in graduate school doing classes in cardiovascular fluid mechanics at Georgia Tech, one of the things we learned were rules where blood clots form, where atherosclerosis or fatty plaques form, and things like that based on fluid mechanics. So like you were saying, the architecture, the location, and the mechanics are all super critical in considering the type of intervention and therapeutic. The architecture is important in determining how we regenerate tissue.
Lots of exciting stuff ahead. So Vivek, where can people keep tabs on your work and see the trials as you're going through them and just follow the company's progress and wait for a clinical application? Where can people go?
So we have a lab website, kumarlab.njit.edu, New Jersey Institute of Technology, right? njit.edu. And that's where you can see a lot of the work that we're doing in terms of novel therapeutics, some of the ideas that we're coming up with. We even have work that we've done against SARS-CoV-2, designed proteins and peptides that target virus. If you want to check out some of the work that we're translating, especially in the angiogenic peptides, there's a company that we've started called Nangiotex, Nangiotx. It's like a portmanteau of nano angiotechnologies, right? Nangiotx.com, nangiotex.com.
Okay. Well, very good. Well, Vivek, again, great call. Thank you for what you're working on. And I really hope that you guys succeed tremendously so you can help a lot of people. And thank you for coming on the podcast.
Thank you very much. I appreciate the opportunity. Thank you again.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.